I do give extra credit
Yeah, back to PLO assignments.
when I can see that you've shown learning, that you have actually done something correctly. And on those PLO assignments, which go bonus point to your homework, I give partial credit, but if you get something wrong, like it's not graded by completion. And that, I think, is what most people want with bonus points, is they want something graded by completion. All right, so our first one was trans 1,2-cyclohexane diol. Which of these conformations was the higher energy conformation? The one on the left is the higher energy conformation. Tell me why. Has more axial groups. Axial positions always creates a minimum of 2 steric strain interactions, the 1,3 diaxial strains. Not to mention other possible steric strains with other groups. But being equatorial has a minimum of 0 and sometimes more. So if we took the Newman projection of the structure on the right, we would see steric strain between the two OH groups. The structure on the right has the groups gauche to each other. If we looked down the carbon-carbon bond where the two groups are, we would see that one is up, one is down, gauche to each other, 1 steric strain. But here, they both have 2 steric strains for a total of 4 steric strain interactions. Oh, okay. So higher energy. And what could we call this one?
High stability.
High stability. All right, for our second one, and remember, or if you weren't here yesterday, that O on the left is supposed to be an OCH3. Remember that this one I screwed up, but there is actually a way to solve it. What we have to do here, because you'll see that both rings have the two groups 1, 3 to each other. And the two rings have the two groups cis to each other. You guys agree that this is cis 3-methoxy cyclohexanol? The two groups are both down. Here, the two groups are both cis. But I told you what Cardi B said. Thank you, Delaney. I almost dropped a beat for you. How can our groups go from down equatorial to up axial? They're supposed to go from down equatorial to down axial. So one thing that we could do is draw a different chair conformation, one where the groups are actually down. So here's 1, 3. I'm going to do the 3 on the back carbon. Here's 1, 3, and they're both down axial groups. That would have been appropriate. I'm going to show you that we can fill it in here. So first of all, OCH3 on the left and OH on the right. Not really by necessity, but because of the orientation of these groups. If I say that I go from alcohol to ether counterclockwise, then I need to go from alcohol to ether counterclockwise. I just need to maintain those same groups. So what I have down here will need to be alcohol to ether counterclockwise, just the same as before. So I have my OH and my OCH3. That's if my groups are pointing down. Did you guys know that counterclockwise and clockwise just depends on your perspective? Did we talk about this on the first day of class? Maybe not. Do you guys know in the northern hemisphere, water rotates differently than in the southern hemisphere? I never remember which direction. I think northern hemisphere things move clockwise and southern hemisphere things move counterclockwise. But what perspective is that from? Imagine a hurricane, and we say the hurricane is spinning clockwise. Is that from the satellite view? Because if I'm on the ground and I look up, it's going to look like it's moving counterclockwise. Or think of the namesake, clocks. What direction do the hands on a clock move? From the perspective of the numbers, what orientation do the hands on the clock move? Counterclockwise. From the perspective of the clock, the hands move counterclockwise. Your perspective determines rotation. You okay with that? Okay, I'm going to pretend to be the hands of a clock. Clockwise. Now, what direction? Counterclockwise. I didn't change anything, did I? I just changed which way you looked at the rotating arm. So, 2 groups down, counterclockwise, 2 groups down, counterclockwise, 2 groups down, counterclockwise, 2 groups up, the relationship from OH to OCH3 needs to be clockwise. All I'm doing is taking this structure on the bottom, I'm flipping it like a pancake, flipping it over. Looks like a trampoline, flip it so it's an upside down trampoline. So OH on the left, OCH3 on the right. 1, 2, 3 clockwise, because your perspective changed. Perspective. I really want to make sure my mic works. Hate it when it doesn't. Lovely. Next, we have 1 cis, 1 tert butyl, 4 ethyl cyclohexane. And what I remember from you guys last class, the main question was, does it matter which one I place on which position? And the answer was no, it doesn't matter which one goes where, so long as they flip in the 2 structures. Because here, I can go tert butyl to ethyl clockwise or counterclockwise. They're directly across from each other, so the relationship doesn't need to be determined quite like this. Remember, we had to do the clockwise, counterclockwise with trans 1,2 cyclohexane diol. Up to down clockwise, up to down clockwise, up to down clockwise. We needed to make sure we maintained that orientation. Here, doesn't matter which orientation you have. It's the same orientation either way. So I'll start with tert butyl up equatorial and ethyl up axial. And then during my chair flip, the down carbon, is it obvious it's a down carbon? Why? It's literally pointing at the bottom of the board. It's pointing down. The down carbon needs to become an up carbon. And there are 3 places I could draw that. It's been drawn for you on this up carbon. Tert butyl stays up though. Up equatorial, up axial ethyl to up equatorial ethyl. Okay, I'm sorry, I'm jumping around a lot. Highest energy conformation for our 1,3. The one on the right.
Oh, this one.
Oh, you're saying this is highest energy?
No, I'm saying the one next to it, where they're both axial.
Yes. 2 axial groups, higher energy than 2 equatorial groups. Okay, actually, here's another an interesting thing to look at here. Trans 1,2 will have both groups up or both groups axial or both groups equatorial. A cis 1-2 would always have one axial, one equatorial in your two conformations. Cis 1-3 mirrors what we're seeing for trans 1-2, both equatorial, both axial. A trans 1-3 would have one group axial, one group equatorial. The structural position of your two groups, or the structural position of any groups, and their stereochemistry kind of impacts what the chair conformations look like. And so here we see that cis 1-4 always has one group up, one group down. So for our first two, I was able to analyze by which had more axial groups. But now, how do I determine the highest energy? The size. Larger size, larger strain. What's bigger? Terp-butyl is going to be that biggest group you're ever going to see. Yeah. When you see a terp-butyl, I want you to think that's the biggest group. That's going to be the one causing strain. So what's my most stable chair conformation here?
One with the terp-butyl in the equatorial position.
Equatorial terp-butyl. High stability. Low energy. Yep. Equatorial points almost exactly along the equator, although you guys might remember from this little ball and stick model, they point up and down a little bit too. Okay. Last one, we need to fill in some of the top-down view. So we're given a blank hexagon. We have an up axial chlorine and up axial aldehyde and up equatorial isopropyl. I want you guys to feel comfortable moving in and out of these bond line structures versus condensed structures. So on your sheet, I gave this as CHO, CHO, and CH3, I want you guys to feel comfortable being able to convert between them because neither is correct or incorrect. They're both equally acceptable. Think about what element is this? What element is this? A little bit different, communicates the same thing. That's the identical idea here. A little bit different, communicates the same thing. All right, so I need to have this relationship. I'm going to start at the isopropyl and just work my way around. I'm going to say 1, 2, 3, 4, going counterclockwise. And I think I'll start by converting from the chair into the top-down view. All of my groups are wedged. So wherever I decide to put these carbons, 1, 2, 3, 4, all of my groups will be wedged. A wedged isopropyl. A wedged aldehyde. A wedged chlorine.
And we're assuming that they're all wedged because they're all in the up carbon position.
Good. I don't know how much I want to use the word assume there. We're interpreting them or translating them as wedged because they're all in up positions. Good.
Question.
Tell me.
You wouldn't want to start at the CHO and on the chair guy and go clockwise because then you would end up with a higher locant set.
We're not naming,
So it doesn't matter.
so it doesn't matter the locant set. I would call this more mapping.
Okay.
I'm assigning numbers. You could assign shapes. could assign colors, you could assign letters, and then I'm mapping those markers into my top-down view. And I'm going to map them into my next chair conformation as well. So all of the times that we're doing these countings, we're mapping our carbons. We're saying this carbon now is here, not numbering. You are correct, though. Well, actually, if we were naming this, the aldehyde has high priority.
Yeah.
So it may have been position 1. Not what we're doing, though.
Okay, great.
Okay. So what I want to do now, especially since I've mapped it, I want to take 1 from being a down carbon and make sure that it's now drawn as an up carbon.
So you'd shift everything over by 1.
I could shift it by 1. I could shift it by 3. Or 1 in the other direction. There's a lot of correct answers here. So I'm going to shift it. Well, I think I'm going to shift it to the right. I'm going to put 1 back here, 2, 3, and 4. And notice that I'm still going counterclockwise with my numbering. Carbon 1 had an up equatorial isopropyl. Carbon 1 now has an up axial isopropyl. Carbon 2 had an up axial aldehyde. Carbon 2 now has an up equatorial aldehyde. If it's hard to see that that is an up equatorial group, one thing that you can do is draw in the down axial hydrogen. Have a line that comes straight down from it. Because we can't use wedges or dashes in these chairs, so we need to infer from the orientation of these groups. Then carbon 4 had an up axial chlorine. Now it has an up equatorial chlorine. If you're going through and you find one of my groups was supposed to move from axial to equatorial, but for some reason I'm drawing it again equatorial, or I'm drawing it again as axial, then you might have numbered your carbons wrong, or you might not have swapped everything from up carbons to down carbons. Which of these is the high energy conformation? Who said the middle one? Because this is actually not a conformation. Do you guys see how this ring is neither conformation or both conformation at the same time? The middle structure is the high energy, yes. But the high conformation, there's only 2 conformations on the board. High energy, low stability. You guys are comfortable with that though, right? That the bond line can give you either one. The bond line, the top-down view does not infer which conformation you have because both conformations are possible.
So that one in the middle is higher energy, despite the larger group being in the up carbon axial position because there are 2 in the down axial position.
Well said. This is higher energy because there are more axial groups, despite the fact that the largest group becomes axial there, or is equatorial here. Because we're always aiming to minimize axial groups. Not always aiming to. Remember, this is a way that we can interpret our bond line, or our 2 conformations. We've got that high energy boat in the middle, and then we have a high energy and low energy. If I have a very cold system and the molecules don't have a lot of energy, they will sit in their most stable conformation. But if I start heating a system up and I start adding energy into the molecule, it's going to use that energy in different ways, and some ways that it uses will be twisting into these high energy conformations. So it's not that one of these is better or worse. I heard a professor once that said, good, bad. No, I would disagree. I don't think this is good or bad. They are not evil or malicious or well-intended either. They are just ways that it can take up space. The reason we teach you this, by the way, is because later in the semester we're going to see reactions where the orientation of the group dictates its reactivity. An equatorial chlorine cannot go through a certain reaction, but an axial chlorine can go through a certain reaction. So if I want this chlorine to go through that reaction, I need to make sure that I pump in enough energy to get it into its highest energy conformation where it's actually reactive. Because if I do it with too little energy, I can never react with it. It doesn't have the spatial arrangement it needs to do the reaction.
So I guess, are you saying based on the environment that these molecules may be in, it will be in its different, I guess, stable form? And depending on how much energy is being put into that system, it can change to become more reactive?
Yes. Another way that we can say this is at any given time, a percentage of a sample will be in both conformations. A percentage will be in transient, dynamic equilibrium. At a low temperature, we'd have a very high percentage low energy conformation. At a high temperature, we'll have higher percentage in the high energy conformation. At any given time, you can assume there's in a sample, there are both conformations happening. And that you can change what percentage that is using temperature.
I imagine typically the high energy version is always more reactive. Probably not always, but
Not necessarily.
mostly tend to be more reactive.
Not necessarily.
Not necessarily.
So in general, we do say something that's more reactive typically has higher energy versus something that's more stable would be less likely to react because it's got all of this potential energy to use. Like we can just say that with my markers. This marker is more reactive because it has all of that potential energy. When I drop these to the ground, didn't do much, did a lot, right? More reactive because of all that extra energy stored in there. When we talk about reactivity in organic chemistry, though, some of the reactivity deals with the functional group. The nature of the functional group can change reactivity. Or we talk about the arrangement in space that it has, like being axial versus equatorial. Okay, here's a change I could make to this. We take this structure and we make it a dashed group, which means it's going to look more like this. Now, instead of the aldehyde and the chlorine always being opposite axial or equatorial, now they actually become shared axial and equatorial. So here they're both equatorial, and now here they would both be axial. This is now a high energy conformation, and yet for the chlorine, this is the reaction that it's allowed to go through those reactions. I'm being very vague about the reaction because we're not talking about it, but I'm speaking specifically of something called E2 elimination, where it forms a double bond between these two carbons. The chlorine has to be up. Now the chlorine is reactive despite being in its lower energy state. All that means to us is if I have a reaction around the chlorine that I want to do, it's going to be a lot easier to do it. It's going to require less energy to run that reaction if the reactive conformation is the low energy conformation. It's going to be harder for me to do it if the reactive conformation is the high energy conformation. Okay. We're going to transition now into talking about the spatial arrangement that everybody loves about organic chemistry. We're going to talk about chirality. So I believe you guys have learned about this in your pre-reading quizzes by skimming and scanning your chapters. Any idea what chirality means? Asymmetry. Chirality equals asymmetry. We have another term, achirality. Symmetry. No, they're not counterintuitive terms. They're antonyms, right? Chirality and symmetry are just antonyms of each other.
But wouldn't achirality, wouldn't it make more sense if that was asymmetry?
That's why I'm saying it's counterintuitive.
Or does chirality actually mean symmetry?
Do you know what an equal signs means, Gavin?
Well, yeah, but I'm saying like Michael said intuitively, shouldn't achirality be like asymmetry?
I think this is my explanation for it. The lack of symmetry is such an important concept in chemistry. The lack of symmetry is such an important concept, it was given its own name.
Okay.
Just like how you think symmetry is such an important concept in the world around you that you gave it a name, the lack of symmetry is such an important concept we gave it a name. Chirality is lacking symmetry.
So that's like the baseline. That's the good thing.
Good thing, bad thing, hard to put that on there, right? It's the perspective. It's the perspective you want to have. Think of the other perspectives we've been having. High energy, high stability. Not good or bad, just different perspectives, right? Having symmetry, lacking symmetry. Different perspectives. Lacking the lack of symmetry, right? That's what achiral means. Lacking asymmetry. And this term, chirality, actually comes from Latin for handedness. Oh, I don't want to do it on that side. Handedness. What hand is that?
Depends on which way it's coming at us from.
Ooh, first time anybody's gotten that. It depends. It's my left hand because I drew my left hand up there, right? It's my right hand because my right hand fits. Okay, if handedness is where the word chirality comes from, and chirality tells us about the lack of symmetry, then why can either of my hands fit in here? Doesn't that kind of lean into symmetry? Your hands, Latin, chiral, your hands are chiral because they lack symmetry. Do you agree that your hands lack symmetry? Go down the middle finger, the pinky does not reflect into the thumb. Go through the fingers, the palms and fingerprints do not reflect into the nails. Go through the palm and the finger, is that the palm? The cup. Go through the knuckles, there we go. Go through the knuckles and the fingers do not reflect into the palm. Your hand lacks symmetry, and because of that, your two hands are different from each other. Your hands are chiral, despite being exactly the same. I mean, ignore the ring. Despite being exactly the same and exactly opposite, Despite being exactly the same, they are exactly opposite. They're mirror images of each other. They cannot be superimposed. If I get my fingerprints to point the same direction, my fingers don't actually line up with each other. If I get my fingers to line up with each other, my fingerprints and my nails don't line up. So we say that your hands are non-superimposable mirror images, and this is a key feature of chirality, lacking symmetry. All right, we're going to come back to this example of the hand in a little bit. I'm going to use it to rationalize some things. But I want to start by talking to you guys about the most fundamental chiral component, which is chiral carbons. Chiral carbons have like 10 different names. Asymmetric carbons, asymmetric centers, chiral centers. Okay, stereo center. I think that's it. A chiral carbon, of course, we can say is a carbon that lacks symmetry. That's already embedded in the name chiral. So instead, we're going to say chiral carbons have 4 distinct groups, are bonded to 4 distinct groups. Not 4 distinct atoms, not 4 bonds, 4 distinct groups. So first of all, this means that we're focusing on sp3 hybridized carbons. And this is a lie, but it's a good lie, believe me. There are deviations. There's exceptions to this. But you'll never look at a trigonal planar carbon. The fact that it's called planar means the top must be symmetric to the bottom because everything exists in just one plane. sp2 carbons are off the table. We won't look at sp carbons, although there are some that are chiral. We won't look at them because they exist just in a line. So the left side of the line must be identical to the right side of the line. The top of the line is identical to the bottom of the line. Maybe the 2 sides of the line aren't the same, but the tops and bottoms and sides are. We're going to look for these 4 groups. So on your worksheet, I've given you this example of a tetrahedral, and it's got positions 1, 2, 3, and 4. And I want to show you how the lack of symmetry actually shows up across mirror planes. By having these 4 groups attached, they take up a very specific arrangement in space. And if I swap any 2 groups, I change the spatial configuration. Configuration changes when 2 groups swap. Do you guys know how weird mirrors are? Mirrors are pretty weird. You know, I'm always driving and I'm looking in my rear view mirror and I see somebody with a blinker on and I'm looking at an image of a car, and if all I could see was that image of the car, I would say that is the car's right blinker that's blinking. Even though it's on my left-hand side, I know that the car itself would be blinking its right blinker. But because it's a mirror image, it is actually the left blinker of the car on the left-hand side in my field of view. Because mirror images swap front and back, left and right, or top and down. Top and down, top and bottom, up and down. Mirror images will swap 2 things, and by doing that, they change the actual configuration of what you're looking at. Elvira, did you raise your hand?
Yeah. I was just going to say that that has been used to cover up police investigations, too, in the past.
Wow. The police are covering up their investigations by swapping the mirror? Or you're saying like
So do you
the police get fooled by people swapping the image?
no, did you guys followed the case of the woman, I can't remember her name, but she ran over her husband in Mississippi, Karen, what's her name?
It's like a daily thing.
No. Anyway, the whole story is like, but anyway, they were looking at the footage in a mirror of
Mm.
the police at the evidence center, and they were taping up a stoplight, and so they were like, look, they're taping the right stoplight, and somebody was like, no, this is reflecting back on the mirror, they're taping the left stoplight, which is all wrong, and ended up proving their case.
You guys watch Doctor Strange?
Yes, my friend looks exactly like that.
And they go into that mirror verse, and I always think about that. You know, what if Doctor Strange went in there and wanted to like steal something from the mirror verse version of himself? I know this is a weird thing to say. He wants to do a heart transplant, and he takes his mirror verse version. His heart wouldn't fit.
No.
The aortic arch would be going the wrong way, right?
Situ inversus is the medical condition.
What is?
Situ inversus, some people are born with the organs on the left side.
Meaning like mirror image orientations of their body?
One of my
Yeah, so
cadavers have that.
So like, the aortic arch normally goes over the top and to the left, but some people are born with situ inversus, which puts the
But that only changes the aortic arch, and it doesn't change all of the valves
No, like
and whatever they're called?
The liver will be swapped as well. So instead
Oh.
of having the larger portion of the liver over the left side, it's over the right side as well. As well as like the orientation of the large intestines and the way they turn, going the opposite way.
Wild.
Situ inversus.
So here we're swapping two groups. Now I'm going to be honest, in trying to tell you which groups we're swapping, I feel like I'm going to struggle. You can see that the 2 is swapping, right? What we're swapping here is left to right. We're not changing what's oriented up and down, but we're swapping what's oriented left and right. So group 2 from our tetrahedral carbon was going to the left. Now group 2 is going to the right. And by swapping the orientation of group 2, I can no longer get these groups to superimpose. And I can try to demonstrate this for you by taking a molecule, and you guys will get the chance to work with these molecules again today. Taking a molecule and swapping two groups. Yeah, that's what I should do. Oh, I'm going to have to rebuild this. Oops. Okay, actually, these are not mirror images of each other. Can you see that? Because the blue and the white don't fit. They are, well, yeah, you're right. So they are actually identical to each other. They perfectly superimpose, which means their configuration in space is exactly the same. So what I'm going to do now is take these two groups, and I'm going to swap it. Achirality. They are achiral to each other. But the carbons, this carbon is still chiral. And what I can see now is just by swapping that blue and white group, I have mirror images. And we're going to talk later about how they can't superimpose and what we call that. But just by swapping those two groups, I went from the same molecule to a different molecule. Now, okay, your molecules, real-life molecules, cannot just pop off their bonds and reorganize them, which means when your molecule forms with 4 distinct groups at a carbon, it matters the arrangement of those 4 groups. That changes how they take up space. Now they are the same molecule, but if this molecule had formed with just those 2 groups swapped, and this time I'll swap different groups. I'll swap the purple and the blue, and we'll see how the configuration continuously swaps back and forth from being different or the same, depending on whether I swap out whether I swap 2 groups. So we can swap groups left to right. We can swap groups front to back, and that's what that second image is meant to show you. Notice how 1 and 2 stay the same, but now I have a mirror plane where 3 and 4 have swapped. This is what you typically deal with when you're looking like in the bathroom mirror. Here's the mirror. 3 is pointing towards the mirror, which means that within the mirror, 3 is pointing back at you. 4 is face away from the mirror, which means that inside the mirror, 4 is facing away from you. So I have swapped back and forth. I have swapped left and right, which means that in the middle, I have a different configuration than what I have on the left and the right. But what about what I have on the left and the right? Are they also different from each other? Two groups, or I'm sorry, two wrongs make a right.
Yeah, because they're just rotated. You just rotated the top axis.
By swapping out left to right and front to back, I have basically not swapped out anything. You guys okay with that? I don't know what I did, but I'm one atom extra. Okay, here we go. All right. So let me give you some cliff notes on achiral carbons. CH3, always achiral. CH2, always achiral. Carbon in a double bond, always achiral. Carbon in a triple bond, always achiral. You'll never have to look at those and decide, are they chiral or are they achiral? So I would like you guys to go through and find on these next 3 molecules. Well, okay, we'll go through the first 3 together, and then I'll have you guys look through all the rest of them. Acetaminophen, ibuprofen, and threonine. Is it threonine or threonine? Threonine. Sure, that makes sense. Yeah, I agree. When looking at acetaminophen, how many achiral carbons, or how many chiral carbons do you think there are? Thank you. I hear 2. How many chiral carbons in acetaminophen? I think that's as many carbons as there are. So sorry, and the question was how many chiral carbons? Okay, I did at some point. Huh? Which one is chiral?
Oh, actually,
Zero.
Okay.
I just looked at that nitrogen and I was like, oh yeah, that's a carbon.
Chiral should be tetrahedral, shouldn't it be? So like,
Yep.
because chirality needs 4 distinct functional groups, and there aren't any.
Well, this is a chiral carbon. I'm sorry, this is a tetrahedral carbon.
Oh, okay.
Didn't I just say? These are all sp2, which means they're achiral. This is a CH3, which means it's achiral. There are 0 chiral carbons in acetaminophen. Sorry, I'm all over the place with the words I'm saying too. That nitrogen has 4 distinct groups, doesn't it? But it's not a carbon. And nitrogen with its lone pair can do a strange thing where its orbital flips. And so the umbrella of nitrogen, the trigonal pyramidal orientation, can actually invert on its own, which means that it's never just oriented one way in space or another way in space. It can be oriented both ways. Actually, another thing, something I didn't get to tell you guys in our Unit 1 that nitrogen is in resonance with the carbonyl. And it's in resonance with the aromatic ring. But the nitrogen can donate its lone pair to the carbonyl, so the nitrogen is actually sp2. And sp2, a chiral. All right, what about in ibuprofen? One chiral carbon? Rowan, you want to say where?
Would it be like, I don't know how to describe it,
The carbon attached to.
like in between the ring and the double bonded.
Here. So let's name the 4 groups. One group is hydrogen, which is assumed.
Yes.
One group is methyl. One group is the aromatic ring with the isobutyl group. One group is the carboxylic acid. 4 different groups. 3 of them are carbon groups bonded to our chiral carbon. But it's not 4 different atoms. We're looking for 4 different groups, and a methyl is definitely not the same as a phenyl, is definitely not the same as a carboxylic acid. All right, so here is one chiral carbon. Now, I'm not going to look at the CH3, I'm not going to look at the CH2, I'm not going to look at the CH3s, but hey, a CH, not on my list. I should investigate it. Is it chiral? Can you tell me why, Evelyn? 2 identical groups, 2 methyl groups. For the same reason that a CH2 is achiral, the hydrogens are in plane with each other. Which means that they create, actually, I'm sorry, my plane of symmetry is wrong. Because the hydrogens are in plane with each other, there's a plane of symmetry that goes between them and reflects in. So the CH2 is symmetric. CH2 is achiral. Now we can do that same thing with methyl groups. We can do the same thing with benzene rings. We can do the same thing with anything. If 2 groups, at least 2 identical groups are attached, no matter how large, symmetric. So 1 chiral carbon, and now in 3, no, you're going to have to say it again. Creatine, threonine. Threonine. Sounds like creatine. How many chiral carbons?
1.
Where is it?
It's in the middle, bonded to the amine.
Looks chiral. It's got a lot of groups. Amine, carboxylic acid, the rest of the molecule, and hydrogen. Where else, Evelyn? The one bonded to the alcohol. The secondary alcohol carbon. Bonded to OH, bonded to methyl, bonded to the rest of the molecule, bonded to hydrogen. 4 distinct groups, 2 chiral carbons. What's the maximum on chiral carbons in a molecule? How big is your molecule? They can all be chiral. They can none be chiral. So go through those molecules below and circle every chiral carbon that you see. I'll come around to answer questions if you have them. Feel free to collaborate, talk with each other.
Professor, how come there weren't 2 chiral carbons? You said because
In what?
on the top one, there's only 1. Because you said that on that left sp3,
Yep.
it's because there's not 4 different groups.
Right. So this carbon is achiral because the 2 methyl groups are symmetric to each other.
Okay, so the groups has to be different types of groups?
It has to be 4 distinct groups.
Okay.
Methyl is not different from methyl.
Okay.
Hydrogen is not different from hydrogen. OH is not different from OH.
Okay. So it has to be like the other one, we have the aromatic ring and the CH3 and a hydrogen and a carboxylic acid. So it's
Perfect.
different. Okay.
Yep. Now imagine, Gavin, if this carbon chain had just been 1 carbon longer. If relative to that carbon, it was an ethyl group. Ethyl is now different than methyl. Those are distinct.
Okay.
That makes the chiral, the carbon chiral.
Thank you.
Absolutely. Good start, Andrew.
So now we have that.
Is this fluorine a separate group? Are you saying all these that you circled are chiral?
Good start.
I'm wondering about that one.
You're wondering about it?
Yeah, but isn't this all the same ring? So, yeah, 2, 3, 4.
I agree with you.
Cyclopentane.
Yeah, kind of. This template of six-membered, 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 five-membered ring is common of steroids. Like testosterone, estrogen, and others, all have that same pattern of 6, 6, 6, 5.
Interesting.
Now, just because the two groups coming off of it are linked back through the same chain, doesn't mean that they're the same groups going in either direction. You could actually try and describe it by detailing what's connected. What is the substitution of the carbon this way, to the left?
The substitute?
Is it primary, secondary, tertiary, or quaternary carbon?
Oh, like going that. Isn't this a quaternary carbon right here?
That is a tertiary alcohol.
Oh, tertiary alcohol.
But what I mean is the group to the left
This right here.
is what type of carbon? Starts with what type of carbon?
Yeah, but so I'm just
Wouldn't
confused about why.
Be quaternary because there's 4 bonds.
Good. Not just 4 bonds, because you're right, this one also has 4 bonds. This is 3 bonds to carbon, tertiary. 4 bonds to carbon, quaternary. What about to the right? As I go down to the right in the ring, what is the substitute? No, other way. From my chiral carbon, or the one I suspect is chiral,
Oh, right here. Tertiary.
is tertiary connected to my chiral carbon the same as quaternary connected to my chiral carbon?
That's a different degree of carbon, so would they be different?
Different. If you can find even that smallest distinction, then they're different.
I think I was curious about the same thing. So is that like the easiest way you'd say to distinguish, like if they're both bonded to carbon groups?
Yeah.
Just
Try and define a difference between them.
Okay.
Hey, a tertiary carbon is different from a quaternary carbon. They must be different groups.
cool.
And you don't have to stop at the first connection. Just keep going until you find a point of difference. Did you have a question, Michael?
Oh, no, I was just looking back at what you were saying earlier
So can you consider, do you consider?
yeah, finding them.
Mm.
So, because like, it only works if it's tetrahedral, right? That's what we're looking for. sp3 tetrahedral.
There's an exception there, but for our class, yeah.
Okay, so like, with this one, dextromethasone, right? I've circled a few suspect ones, but there are also like, right, like, this one right here, I wouldn't assume would be. I know there's then implied hydrogen, but as the rest of the structure continues, because they're connected, it's not. But it doesn't count if the.
Well, we have to prove that the groups are different. So what proofs can we give? Well, these are both alkane-like carbons, but that's a tertiary carbon, and this one, right, just from the first point of connection.
Yeah, tertiary because it's got the 3 other bonds.
3 bonds to carbons. So that carbon,
It's tertiary, this is tertiary.
you're right. So one of the groups, you think this might be chiral. One of its groups is a tertiary carbon. Another group is,
Tertiary, well, a secondary.
okay, well that's different.
Oh, I see what you're saying. This one right here, with this drawing, this is coming up, this,
It's not wedge or dash.
okay, but it's
Yeah.
coming off the carbon.
It is.
So
Yep.
this is a 4th.
Yeah.
carbon.
Because-
It's got 1, 2, 3, and then a fluorine.
Well, so that's a tertiary
Tertiary.
alkyl halide.
Okay, so it is different.
Yeah.
So
Yeah.
okay, that would count. That's okay. That's
Tertiary alkane, secondary alkane, tertiary alkyl halide, and hydrogen, 4 different groups.
Okay, that makes more sense. I got 2. Thank you.
Yep. By the way, is counting chiral carbons regiochemistry or stereochemistry? Yeah, you're looking at what's in the region around it. Are they distinct groups? You're looking at its regiochemistry. And then Quinn said stereo because chirality has to do with spatial configuration. So the regiochemistry is now having implications in the stereochemistry. I love it.
Okay.
I'm going to answer Jacob's question first. Did you raise your hand?
No.
Oh, I'm sorry. I saw his hand.
Crazy. Okay. What
I'm crazy?
No, that was crazy. What am I missing here?
I only counted 1 too.
Who says you're missing anything?
I just feel like I probably am. Yeah.
What? You think because a molecule is massive that it has to have a lot of chiral carbons?
Oh, I think I don't know what's going on.
I think you got all of them in both dexamethasone and ipamidazole.
Iopamidol.
Iopamidol.
So this is like this
Looks
guy
like it.
is chiral because this carbon is connected to this, which is not the same as that, which is not the same as that.
Yeah.
Which is not the same
And
as
this
the
is a
hydrogen.
pent, cyclopent.
Sure.
form, and this one's cyclohex.
Sure. Yeah.
So like, you know
Well,
the difference?
actually, another way you can say the difference is this carbon is bonded to a tertiary carbon, a quaternary carbon, a secondary carbon.
Nice.
You know what that means?
Yes.
Bonded to 3 carbons,
Yes, I
bonded to
do.
4, bonded to 2.
Yes.
It is a cyclopent and a cyclohex, although a lot of people would look at this 6-membered, 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 5-membered complex and say that's a steroid. So they wouldn't look at it and say, I've got a cyclohexane or a cyclopentane. They would look at that as a total, a whole and say that's a steroid.
I didn't know what that meant. That's
Yeah, like testosterone and estrogen have a very similar base structure.
Okay. Did you guys
have 9?
fentanyl? No.
Yeah, I don't remember the numbers, but
No, I got 1.
I think there's 2 that are not.
This is bonded to the same as this. They're both CH2 groups.
Okay, if you haven't already, get into groups and see if you agree on the number of chiral carbons for each molecule.
Looking at the, I think this is all the ones for dextromethane.
I don't.
I'm missing one.
You're missing more than one.
More than one. I'm trying to think. So, oh, you know what? This one would be right as well
I agree.
because of the carbon there. And
You're still missing more than one. See if Patrick and Andrew can help you.
I don't think you can put any of the ones attached to the double bond.
I agree. Because those sp2 carbons are achiral.
So you go all the way until the difference. So symmetry will go all the way until those different.
Yes, until the point of difference.
What that's what I meant.
So with chiral carbons, we have to count the whole molecule, even if we're looking at one of them.
Yep.
Okay, 'cause that's what I'm doing.
How many you got? 9? 8?
Every carbon that isn't the top left hydroxide.
Yeah.
That tertiary carbon next to quaternary and secondary.
This carbon.
Okay, so you're saying that's the reason
I think
that's
Google's wrong. Google has to be wrong.
Definitely don't think it's gonna work.
Nitrogen of
I don't think there's even one.
I wonder if that's
I
all.
can see the one.
It's zero.
It is 0.
Yeah.
Pretty solid.
My,
I was like,
is
where
that
did you
like
get this?
benchmark of the? Is that like what we did like first day of class?
think I messed up on sucrose's structure.
Has not.
I also see why that was also wrong.
Fentanyl has
Yeah, fentanyl doesn't count. I'm glad you put fentanyl, that was my choice.
And I didn't steal that one from you, Michael. You're just not the first one to do it.
It's a good molecule.
I agree.
I don't blame anybody for choosing that compound.
Again, molecules don't have good or evil. So despite fentanyl ravaging our communities with drug abuse and stuff like that, it's not fentanyl's fault.
Nobody, when Anakin killed all those young ladies, nobody legalized it.
Right. And guns don't kill people. Cars don't kill people. People kill people with weapons. Ban spoons. Maha.
I was spent most of that class being in genetic expression.
I would agree.
Junior kid I was from Chiral Elementary.
That's nice. It's better than using fentanyl, I guess.
Even the ones that like
You go to high school here?
Utah? Yes. I went to
That tracks. Yeah.
No, Harriman Thor would kill yourself.
All right, let's come back together and decide on how many chiral carbons we see on each. Dexamethasone. By the way, does anybody know what this does?
It's a steroid that, it's an well, they use it for altitude.
An altitude sickness steroid. Okay.
It's like superhuman.
Oh, so you'd take this if you were like doing a 14er hike,
Well, you aren't.
Mount Everest hike.
You're not supposed to take it like prophylactically because then if you get hay for haze, high altitude pulmonary edema or high altitude cerebral edema, it like you compensate and then you get it and then you die.
I see.
But if you, it shouldn't be taken prophylactically.
Yeah, okay.
But then if you do get it, it's what you get treatment for.
So it's a treatment, not a preparation for high altitude
They use
sickness.
it as a preparation and it is awesome. You feel like you could like do anything.
Sure.
But it makes you really sick.
So one thing you mentioned there was that it's a steroid, and that steroid structure is 6-6-6-5 membered rings. That is a very common organic structure that you'll see in biological chemistry. Of steroids. Testosterone shares the same template structure. Estrogen shares the same template structure. What else? I can't think of any other. Are those steroids even? Those are, I know they're hormones. Prednisone. What? Maybe androgen as well. There are so many molecules that share a very similar base structure. How many chiral carbons?
8. I got 8.
Okay. Let's see the ones you guys were confident on. Tell me the two.
The one connected to the fluorine, right there.
Did you guys agree on that? I want to start with the people that had the least. Because everybody that had 8 probably also had those two.
We said the one connected to the alcohol above.
Oh, sorry, this one. Okay, those were the 2 chiral centers that you found. Okay. Now, those we can say have a hydrogen, an alcohol, a secondary carbon, and a tertiary alkyl halide, 4 distinct groups. An alcohol, a carboxylic acid, a ketone. It's not a carboxylic acid because the OH is not attached. A carbonyl carbon, an alcohol, a quaternary carbon, and a tertiary carbon. 4 distinct groups. Now, people that had more than that, where were yours? Actually, it might be easier to say what wasn't chiral.
Oh, okay. Yeah.
CH2, CH2, achiral.
Anything attached to the alkenes.
All the double bonds are achiral.
The one attached to the alcohol at the end of the ketone, so that last part.
Achiral. Yep. Good. And then the methyl groups, achiral.
Yeah.
So everything else was chiral. So here, I have a chiral carbon. Now, let's use our regiochemistry terms to prove that it's chiral. Bonded to a hydrogen, a primary carbon, a secondary carbon, and a tertiary alcohol carbon. 4 distinct groups. Quinn and Liana and Rowan, you guys agree back there?
Yeah.
Chiral?
That does make sense.
To the left, we have a quaternary chiral carbon, which is bonded to a tertiary alcohol, a tertiary carbon, and a secondary carbon, and a primary carbon. 4 different groups. And we don't have to work very hard to decide that they're different if we apply regiochemistry terms that we have, like functional groups and degrees of substitution. Surprise, surprise, that's why I taught it to you. Elvira.
Because that's why you don't say 4 different atoms.
That's why we don't say a chiral carbon has 4 different atoms. We say a chiral carbon has 4 distinct
Because
groups.
those don't have 4 different atoms.
Exactly.
They're all carbons.
All carbons. That is a quaternary chiral carbon. And there's not a lot of quaternary chiral carbons, but it's not impossible. Absolutely. All right, CH2, achiral. Here's a tertiary carbon that is bonded to a secondary carbon, a quaternary carbon, a tertiary carbon, and a hydrogen. That's chiral. And then here's my tertiary alkyl halide bonded to, did I mess up on my, I'm missing a methyl group. Yep. Yep. So alkyl halide, tertiary alkyl halide bonded to quaternary, tertiary, and secondary alcohol and fluorine. And then to its left, my last chiral carbon. No, it's not. sp2 on the top of the ring, sp2 on the bottom of the ring. Boy, aren't those the same? Yep. Down here, my sp2 carbon has an extra bond going to the other ring. To the right, it doesn't have any extra bond going to a ring. Those are different groups. And then on the inside, I've got that last tertiary carbon bonded to a tertiary alkyl halide, tertiary alkane, secondary alkane, chiral. 1, 2, 3, 4, 5, 6, 7, 8. Which is like half of the carbons or more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. No, it wasn't more. But a good number of those carbons were chiral. All right, let's keep going with sucrose. And I fear I messed up on sucrose. I think that there's another carbon coming off of this, but it doesn't really, I think my structure is wrong, but it's not going to change the chiral carbon count. How many chiral carbons did you guys find? 1, 2, 3, 4, 5, 6, 7, 8, 9. How many got 9? Okay. How many did you guys got? Andrew got 6. What other numbers did we get?
I got
8. 8? Missing just 1. Any other numbers? For those, Gavin, how many did you get?
Oh, it's exactly what you said.
Yeah, I agree. For those of you that got 6, which 3 did you miss?
Also, the one that's connected to the 2 oxygens, the 2, aren't those connected to the same group?
No. They're definitely bonded to the same atom. Do you want to explain it, Elvira?
Because you go to the point of the difference. So
Yep.
if they're bonded to the same atom, then you say, okay, what's beyond the atom? And then those are different.
This oxygen is bonded within this ring. This oxygen links to a different ring. So there is no symmetry between those 2 groups, which means the carbon lacks symmetry. So that's one of the carbons that you guys missed. What else?
I missed the one on the left side connected to the OH. Nope, down that one.
Right in the middle, which is kind of reasonable because if you drew a line straight up, if you looked for a plane of symmetry, it's a carbon with an OH, and on both sides is a carbon with OH. And then as I go up, both of those carbons connect to the oxygen in the ring. But this CH2OH is very much different from this oxygen to the other ring.
So when you're looking at this, that left half of the ring say, well, I know that all 5 of these are chiral because if I drew a line down the middle and folded it in half, it wouldn't match?
Yes.
Does it have to be chiral?
If I drew a line right down the middle,
Right.
especially because I'm going through that oxygen, so the oxygen doesn't have to reflect anything,
Right.
I do not get the same thing on the left and right. Do you guys remember doing butterflies in first grade?
Yeah.
You draw half a butterfly and paint it in, and then fold the paper over, and now you've got a full butterfly.
Really?
That's symmetry. It's okay. Maybe for lab one day we'll do it.
Like with the glitter glue?
Sure.
Yeah.
Oh, that was the thing.
You get a symmetric structure because you took exactly one half and just copied it onto the other. If you can cover up one half, redraw the half that you see, and get the structure you started with, then there's symmetry there. Otherwise, you can't. All right, so what did we say? 9 chiral carbons. What about down here? What's this guy? Iopamidol. How many chiral carbons?
1.
See, it does not matter how big or small your structure is. The number of chiral carbons is not guaranteed. Did you guys all get that? How many didn't find that chiral carbon? How many found more than that? Okay, so you guys nailed it. And our last one, fentanyl. 0 chiral carbons. CH2, 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 CH2. Did I mess up here? Is that a nitrogen-nitrogen bond? No. That's supposed to just be a carbon in the ring. And now that, I heard some of you, was suspect for chirality. But here's that idea of being able to draw a line, and that's a terrible line, draw a line straight through the structure and get this reflection in the ring. Or another way we can say this, look at the 2 groups that are the ring. CH2, 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 nitrogen. They converged. The 2 groups converged at the same point at the same time. And because I can draw this plane of symmetry through the ring, the carbon has a plane of symmetry, which means that it cannot be chiral if the carbon lies on symmetry. Now, one thing that some people would say is, I don't like how this plane of symmetry goes beyond and doesn't reflect the phenyl into the carbonyl of the amide. I hear you. I can actually rotate this structure so that these 2 groups around the amide stand up directly in that plane of symmetry, and they just get sliced in half. But I can also stop right with just my ring and just consider, is there symmetry in my ring, just for that carbon that I was curious about. Okay. Now, back to this idea of the hand. If a chiral carbon can be arranged differently in space, then how do we know what arrangement we have? I want you guys to try and brainstorm a set of rules that you could give someone to foolproof always tell them which hand is there. Why don't you take 5 minutes discussing groups, as few of rules as necessary, that you could tell someone to help them describe. Let's say they cannot see your hand, but they can feel it, or they don't know the difference between left and right. But if you give them a list of rules, they can tell whether this is your left hand or your right hand. Okay? Take 5 minutes discussing groups. What could you give someone to determine your left from your right hand?
What, back hand on the board?
Yes. Yes. How could you make that left or right always?
The only distinction.
But that's the case for both hands, right? Because you pronate or supinate both hands.
Do you guys want to scoot into this group?
Yeah, right, exactly.
do they need to? We're telling them whether we're looking at our left hand or our right hand, so I think it's safe to say they don't need to know what left or right is. You know, can they tell Frank from Gary? That's
If the left, on your hand,
doesn't need to be named left and right.
the thumb is on the left.
Left.
Okay, I see what you're saying.
You got an idea?
So your left hand,
30 seconds. Can I hear some of your ideas? Liana.
I would just say that they should take their right hand and then grab the other hand, and if it matches up, it's the opposite, and if it doesn't, it's your hand. It's the same.
Okay, maybe
How do they know which hand is their right hand if they don't know right and left?
maybe I should have clarified. Could you give me a list of rules that would definitively tell me whether that is my left hand or my right hand? Because we already agreed we can't tell the difference right now. Yes, you're right. Take your hands, and if they can grab each other, they're opposite hands. I agree. Your hands are different from each other.
I thought you were getting like a tabletop perspective.
That's the pageant answer. Yeah. My favorite date is April 20th. Not too hot, not too cold. Elvira.
Whether or not you can see fingernails.
Can you see fingernails?
Yeah.
Okay, so do you have a list of rules? That's not really a rule.
If you can see fingernails, it's the left hand. Otherwise, it's the right hand.
But I thought we couldn't see.
But it's just depending on that.
For this one. Okay.
Isn't that what you're asking?
Yes. So, but now do those rules apply all the time now? So that's just like, for this one, if you see fingernails, it's your left hand. If you see fingerprints, it's your right hand.
Right.
Now can we elaborate on those rules to make it always applicable? Michael. I'm sorry, it's not like you guys are doing a bad, actually this step is great. I love this step up.
our group came up with the idea that if you put both hands out or a hand out and palm down, if your thumb is sticking to the right, then it's your left hand. But if it's the right hand, the thumb will be pointing left.
Okay, start by putting your palm down. And then look at the direction that your thumb is facing. And you're right, we don't need to know the difference between left and right. So we could say if your thumb points at your heart, or toward what?
I just said toward your body.
Yeah, but it's always gonna point towards your body. So if it points at your heart, that's your right hand. If your palm is down and your thumb points away from your heart, that's your left hand.
So we know where the heart is, but we don't know left and right.
We don't need to know left and right, but you are right, we need to know where the heart is. So here's my list of rules. You guys did great with this activity. Here's my list of rules. Place your palm away from you. This is similar to yours, place it down, so that you can see your fingernails. If the orientation from thumb to pinky is counterclockwise, that's your left hand. If the orientation of your thumb to pinky is clockwise, that's your right hand.
But again, you know what counterclockwise
Yeah, wait, I thought clockwise was a perception-based thing, so doesn't it depend which way you're standing?
Yes, which is why I said palm away. You have to start with your palm away, because if you flip that, if you're looking at your fingerprints, thumb to pinky is still counterclockwise, but that is your right hand. And here's the deal with these rules. They can be manipulated. Rule number 1, place your palm away, thumb to pinky counterclockwise left, thumb to pinky clockwise right, And then if you can't do that, for whatever reason, your hand does not point away, and you have to point forward, your perspective is flipped. If flipped, oh my goodness. You're right, like this handedness wouldn't have come about as a term if we didn't have hands, right? If your perspective is flipped, assign the rotation opposite. That's the deal. If you can't orient your palm the right way, then you just flip your perspective. So here, it looks like I have my left hand, but my perspective is wrong, so it's actually my right hand. Because I broke that first rule and I have my perspective wrong, it's actually the right hand. All right, now how would you assign that?
Oh.
Looks like a nasty foot. How can I assign my orientation? I can't, because I can't go left, or I can't go clockwise or counterclockwise anymore. This is one that I just cannot assign, NA. So the rules that we're going to follow are called the Kahn-Ingold Prelog rules, named after 3 dead men. And then the names that they established, or the rules that they established for chiral centers. Because it doesn't matter that we call our left hand left and our right hand right. That is irrelevant. We could call all of our left hands dominant and all of our right hands recessive, even though that's opposite for the majority of the population. It doesn't matter that we give them the names we do. So these scientists wanted to assign a name. And they assigned names R and S. Those were the names for the chiral carbons, the configuration of the chiral carbons, the different ways they can take up space. And to assign these, they said first, prioritize groups by highest atomic mass at the first point of difference. Group 1 has the highest atomic mass. Group 4 has the lowest atomic mass. Why are we only going to 4? Yeah, it's to 4 distinct groups at our chiral carbon. Okay, so that's rule number 1. Rule number 2. Place priority 4 backwards, away from you. With priority group 4 placed away. This is what you guys were getting at by saying place your palm down. This is what I was getting at by saying place your palm away. Assume a perspective. And I don't mean assume as in like, I can just pick one. But I mean, get to that perspective. Orient in such a way that your 4th priority is back. Sometimes that means rotating through a conformation. You guys remember how we took from zigzag into zig-zig, and we saw groups that were wedged become groups that are dashed. Groups that are dashed become groups that are wedged. That's what this means. Orient, priority 4 backwards. Then determine rotation from 1 to 2 to 3. We ignore priority 4 because we already know where priority 4 is. This is like saying put your palm away and then go from thumb to pinky. I'm not paying attention to the palm anymore because I already know where the palm is. So now that we've determined rotation 1 to 2 to 3, assign a clockwise rotation as R and assign a counterclockwise rotation as S. I'm going to draw that again a little bit bigger so you guys can see it more clearly. If your rotation is clockwise, notice how it makes the upper part of an R. If your rotation is counterclockwise, notice how it makes the upper part of an S. That is not how they decided it. R is Latin for roto something, meaning right-handed. S is Latin for sinister, meaning left. Did you know that cultures all across the world, have this stigma against left-handedness?
Seemingly out of left hand.
I spent some time in Dubai and was like invited to share meals with them, and they said only eat with your right hand because the left hand is for like hygiene things, so you don't eat with your left hand. That is like the right hand is the clean one. Or how school children in America used to be whipped on their hands for writing with their left hands up until like the 40s or 50s. Physically beaten for being a lefty.
My mom would get hit by a ruler.
Yeah, on the knuckles by a nun
Yeah,
in England,
in like England, yeah, in this Catholic school.
all over the world. Sinister is left-handedness.
No, they something right.
Yeah, we just did something right.
So this is chirality. This is how we'll assign whether the chiral carbon takes up one spatial configuration or the other spatial configuration. Not necessarily good or bad. So let's do it with methamphetamine. Because the one chiral carbon in methamphetamine can be arranged two different ways. Do you guys see how the difference is just swapping the placement of the amine and the hydrogen? Remember we said we swap two groups and we swap the configuration? I've kept left and right the same, but I've swapped front and back. And so I have two different configurations of that chiral carbon. One of these configurations will ruin your life and drag you into addiction. The other configuration will open up your nasal passages and help you breathe better. One of these configurations is the active ingredient in Vicks Vapor Rub.
And Allegrity.
And what? Allegrity, allergy stuff. The other, could you imagine if they accidentally synthesized the wrong structure, or if they had both and they didn't separate it? We'd all be addicted to Vicks Vapor Rub. So the smallest difference makes the smallest change in the molecule makes the biggest difference in the world. This would be like if you had a glove, and one hand you put the glove in and you cure cancer, and the other hand fits into a glove and you detonate nukes across the world. That is the only difference between these molecules, is their arrangement in space. And yet what they fit into and the mechanisms that have in your body couldn't be more different.
I was very interested to learn that escitalopram is the S enantiomer of citalopram, which is Celexa versus Lexapro.
Right.
But that hence the S.
Yes.
I don't know why they put
Lexapro.
escitalopram.
Lexapro is for L, which is related to R, or like Levioso or something. And the S is still back to sinister. Yeah. All right, so let's look at this chiral carbon. What is the highest priority group? The nitrogen. This chiral carbon is connected to nitrogen, carbon, carbon, and hydrogen. Highest priority is nitrogen. The lowest priority? Hydrogen. Then the two carbons have the same atomic mass. So we look at the next point of difference, or we look for a point of difference, and we look at the highest atomic mass. From my carbon on the right, the next highest mass is just hydrogen. From the carbon on the left, the next highest mass is a carbon in the benzene ring. Another way that we can say this, a primary carbon versus a secondary carbon. A secondary carbon has more carbons attached and will have a higher atomic mass at a first point of difference. Priority 2, priority 3. Hey, look at that. Priority 4 is already pointed away. So rotation from 1 to 2 to 3 clockwise. This is an R absolute carbon, absolute configuration. We knew it had a chiral carbon. And actually, this drawing that has no wedge and no dash cannot be assigned R or S because we have no wedge or dash to put forward or backwards.
If the nitrogen and hydrogen are switched like in the other one, you just leave it and then just like draw your arrow, but like just go the opposite of it.
Exactly. So I could do one of two things with this structure on the right because the nitrogen is still my highest priority, the hydrogen is still my lowest, the secondary carbon is still my second priority, the primary carbon is still my third. But I've broken rule number 1. My lowest priority group is not facing backwards. My lowest priority group is facing forward. And when I assign this rotation, it's still R. And I know that it has to be a different configuration because I broke my rule. Do we need to tell the numbers on the clock that the hands don't actually move counterclockwise? No, they know already. They've been dealing with this stereotype for a long time, that their perspective looks counterclockwise, but everyone else calls it clockwise. I know that my orientation is backwards, so I lean into it.
So the arrow would go from 1 to 3 instead of S or no?
No, we always determine rotation 1 to 2 to 3. Oh, I'm sorry, I said I broke my first rule earlier. I meant I broke my second rule.
Oh, okay.
Yeah, that's confusing.
Okay, which is the fourth group? The one off of the nitrogen?
No.
Where is it?
Where is it?
I thought number 1 would be number 4.
The highest mass would be the lowest priority.
But it's backwards.
That's what he
You would
said.
have to
It's breaking
redraw
the
it so the
second rule.
nitrogen is coming at you, but you could also just
Right.
like say, since I broke the rule, it's allowed.
That hydrogen is the fourth group.
No, the hydrogen that's not drawn, the assumed hydrogen.
Is the one coming at us the wedge
Oh.
carbon?
No.
But it's number 4 because it's the lowest priority group.
Well, it has to be the hydrogen attached to carbon because that's the chiral carbon. And this is all about the chiral carbon. No, I didn't draw in that hydrogen because I didn't need it. I can assume that it's there. Someone was asking a question I missed. I could do something to take this drawing and flip it like a pancake so that my highest priority is forward, so that my lowest priority is backwards. But that takes a lot of effort. If I can just recognize that I broke rule number 2 and recognize that I'm just looking at my orientation wrong, so this is what I call tip number 1. If priority 4 is forward, then determine rotation clockwise or counterclockwise, but assign opposite.
So if you flipped it, the rotation will be counterclockwise R.
Right.
Okay.
No, sorry. If I take this and I flip it over, can you see how 1 to 2 to 3 flipped over is going to become 1 to 2 to 3 S?
Yeah, we're just assuming that we're looking at it on the opposite side.
We're looking at it backwards. Let's go into the room behind us and let's look at this orientation from the room behind us. What way will it look?
But then,
then the
flip
nitrogen
it,
would be
wouldn't
coming at us.
nitrogen be coming at you?
Sure.
So wouldn't it be R?
No, it looks R right now.
You're running it.
If I flip this over,
Oh, so R is based off rotation, not whether it's coming towards you.
There was like 2 videos.
if I flip it over, do you see how my methyl and my phenyl groups swap sides? I've flipped it over. So now here's priority 1, priority 2, and priority 3.
Yeah.
It is S.
Oh, I see. So basically,
That's exactly what it is.
flips
I almost fell asleep
the
last minute.
groups, but this is the second way of drawing the same
I
thing.
love it.
This is the molecule on the right, drawn so that rule number 2 is followed. But if you don't want to redraw it, you don't have to redraw it. Like in this example, I told you, put your palm away. And then what did they do? They put their palm towards me. Okay, I'm just looking at it backwards. So whatever rotation I thought I had, I'm looking at it backwards.
This is determining if it's an R or an S chiral carbon, right? Based off of the groups around it.
This is assigning absolute configuration R or S.
It's based off,
Fine on the
if
quiz,
we're saying
but
it's
I
for
feel
the
like
chiral carbon, but we use the group around it to determine that.
Correct, we're assigning something about the chiral carbon,
Yeah, that'll do it.
and the something about the chiral carbon is impacted by the groups around it. Exactly. Thank you guys for your time.